11 Lab for Oscillations. So the purpose of this lab is to observe and analyze the motion of an oscillating spring mass system and also to demonstrate the law of conservation of energy. We will be using Tracker to track the observed motion of the spring mass system, and then we'll use GlowScript to develop the computational models to graph the system's motion and its change in energy, which is 0. And that's the sneak peek of the results because the law of conservation of energy is proven. Thus, there is no change in the system's total energy, or net energy equals change in energy equals 0. So the fundamental physics principles, again, Newton's second law, states that the net force is equal to dp dt, or the change in momentum over the change in time. And then we can parameterize the forces. So we have the spring force component and we have the gravitational force component. And then we'll also use the velocity update and position update formulas, as well as the energy principles from the law of conservation of energy, such that kinetic energy equals 1/2 mv squared, gravitational potential energy equals mgh, and potential spring energy equals 1/2 x squared, 1/2 kx squared, and the energy equals work of its surroundings plus q. So the tracker setup will be, the system will be the mass, the spring, and the earth, and the surroundings we will assume there will be no surroundings. The initial conditions that were shown in the video are that the mass equals 0.402 kilograms. I found this R value to be the initial position, and we know the initial velocity will start out as 0. The current spring length is 0.70 meters, but it can be stretched to as much as 0.123 meters. And here I have found the K value, which is 6.875. So here is the GlowScript code. So I put in the initial conditions such as the ball's mass, position, and velocity. And I also put in the spring constant here of 6.875, as well as the relaxed length of the spring, which is 0.123. Then we can update the spring length by these three equations right here, which updates using L naught and such. And then also these 4 lines right here represent the energy principles that I was just mentioning. And then to update these energy principles, all we do is update the velocity and position using the velocity and position update formulas. And those formulas are given by calculating F net, which is F gravity plus F spring. So these are the 3 graphs that I got. The first one demonstrates the change in energy versus time, and the latter 2 represent the change in x position and y position in respect to time in each of their graphs. So the reason why there might be some slight sources of error is that it's not a truly isolated system. Like, you can actually, theoretically, this is only a spring, mass, and earth system, but that's not the case in reality because there's always going to be external forces acting on the system, so it can't be isolated. And also, the tracker could have been inaccurate when I clicked the point masses for selecting the positions. Okay, so these are the what do you mean questions. So for your model system, is the energy principle satisfied? Yes, it is satisfied because the change in energy delta E, which is this orange line right here, it remains at 0, which means that there is no change in energy. And then compare the x direction versus y direction oscillation. So for the x direction one, I got that the period is about 1.67 seconds, and the spring constant value turns out to be 5.691, whereas in the y direction, the period is around 1.5193 seconds, and the K value is 6.875. So from this data, we can understand that choosing different directions changes the oscillation period, and when you change the oscillation period, since this is directly related to the spring constant value will change. All right, thank you.